So I think we should get started.
Yeah, okay, so our first speaker tonight is Matteo Cantiello. So Matteo is a researcher at the Kavli Institute of Physics at UCSD. He's also the chief scientist for a collaborative web project called Authoria, which is trying to get scientists to be more collaborative and open source with their research. And when he's not doing physics, I hear that he's busy building Burning Man projects. So without further ado, Matteo, you can come up and tell us about the sound of stars.
Thank you. Wow, what a crowd. Doesn't make me nervous at all. So tonight, my job is to tell you a story. It's a story about stars, music, surfwaves, and watermelons. Now, you might start thinking a little bit about how those topics really go together, what they have in common. And I'll promise that everything will be revealed, everything will start making sense toward the end of the talk, and maybe a few drinks down the road. So, being Italian, I like to start on a romantic note. I'll start with the starry night, the starry sky. This is, think about it, this is the only spectacle that every human being who ever walked the surface of Earth has witnessed almost unchanged since the dawn of time. Every man and woman has watched the stars, and at least once in their life they felt this incredible feeling of being very small in the universe, being maybe very irrelevant for what is the big picture. And yet, there is a reason why that shouldn't be the case, why we should all feel more connected to the stars and their inner workings. And this reason is something that scientists discovered in the last 100 years or so. Stars are actually shining because they're powered by powerful nuclear fusion reactions in their cores. So in the cores of stars, at very high temperature and densities, light elements are fused into heavier ones. And this produces huge amount of energy. As a matter of fact, the nuclear fusion, the nuclear fuel energy density content is millions of times higher than the energy content density of any fossil fuels that are used on Earth. So if we were to master what stars know very well to do, we will completely solve the energy problem on Earth. We know how to do nuclear fusion, we don't know how to control it yet. But this is definitely something we're working on. But back to the stars. A star like the sun, takes like hydrogen and fuses it into helium by producing a large amount of energy. The hydrogen and helium actually were produced by the Big Bang back in the days, back like 13.5 billion years ago. But all the other elements, especially the one we're made of, they were not produced by the Big Bang. They're actually the ashes of this continuous energy production that occurs inside stars. So as stars shine and illuminate the universe at large, they produce all the elements that we are made of. All the biological life we know and we're aware of, it's in a sense built on the bricks that are left over of billions of years of evolution of the previous generation of stars. At the same time on Earth, the biology is also powered by the energy coming from the sun, our own star. As a matter of fact, all the fossil fuels that we use are actually, in a sense, created, it's energy that has been stored in sort of biological batteries by the sun. So when we burn fossil fuels, we're actually slowly releasing energy that's been accumulated on Earth and was coming initially from the sun. So the ingredients of life, everything we're made of, come from the stars mostly. DNA, for example, made of carbon, oxygen, nitrogen, phosphorus, and some hydrogen. We're mostly made of water, so oxygen is in large part composing our own bodies. The Earth is made of all these heavy elements that came from the stars. Now, the stars are also the building blocks of the universe. So the universe is fairly empty, but wherever you look, when you see light, there are stars there. Our own galaxy, the Milky Way, is a huge stretch of gas, dust, and stars, which is about 100,000 light years across, and contains about 300 billion stars. The Milky Way is not the only galaxy in the universe. As a matter of fact, if you look very deep in the universe, you start seeing galaxies everywhere. This is an amazing picture taken by the Hubble Space Telescope. It's the Hubble Deep Field. In this picture, which is actually just looking at a very tiny patch of sky in the, smaller than the size of the full moon, you can see thousands and thousands of galaxies. All those are islands of stars that are very far away and contains hundreds of billions of stars each. And in the universe, there are about 100 billions of galaxies. So there are 100 billion galaxies, each one containing several hundred billions of stars. Which means, if you do the math, it turns out there are more stars in the universe than grain of sand on every desert and in every beach on Earth. Think about that. The other interesting fact is that when you look at a grain of sand, it's actually mostly made of silicon, and that silicon also came from inside the star. So it's a big circle. It's all coming back to stars. So I hope I convinced you that stars are pretty relevant and are an interesting topic of investigation. And learning about stars, it's a good way to reconnect those vast distances in the universe that seemingly don't care about us. Well, maybe don't care about us, but we do care about the stars because that's where we come from. Now, so if you want to learn more about stars, the immediate step is looking at the closest star to us, which is the sun. The sun shines, and we can look at it from a close distance, about 150 million kilometers, about 90 million miles in the US. These are basically, the star, as you can see, it's much bigger than the planet Earth. You can see planet Earth up there. The Earth is about 100 times smaller than the sun in diameter. And you can see the sun is very hot. At the surface, it has a temperature of about 6,000 degrees Kelvin. It's also very patchy at the surface, and those patches are basically regions of convection. And we'll get back to that in a second, what that means. Most importantly, when you look at the sun, you only see the surface of it. Those regions that we talk about, those very high temperature regions which are inside the sun, that we can only sketch about, are the regions where all the action occurs. These are the regions where the nuclear fusion reaction that produce all the elements we're made of, and where all the energy that makes those stars shine come from. And we are unable to access those regions. Think about it. Those regions have temperature that are as high as 10 or 20 million degrees. And there's no way we can send probes down there. There's virtually no way to get there. These are the most inaccessible places in the universe. So how do we go about learning about these regions? Well, we have a similar problem on Earth, if you think about it. The Earth is several thousand miles across, and yet people have been only able to scratch the surface and dig holes as deep as 10 miles. I think that the deepest hole that mankind has ever dug is about 10 or 11 miles, and I think it's in Russia. Jules Verne dreamt about going there, but nobody is really able to do it. And so we have a way, however, to explore the inner regions of the planet, and this is called seismology. So what do? You piggyback on the fact that there are earthquakes on Earth, and an earthquake is basically a perturbation that sounds the planet. It makes the planet ring for a little while. The sound crosses the planet in the form of sound waves, and as the sound waves emerge at the surface, they tell you something about the region they cross. This is a sort of ultrasound that you do to the planet, and that allows you to know something about the inner regions. For example, we now know that the core of the Earth contains rapidly rotating ion core. The question is, can we do something like that with stars? Well, to do something like that, we need something like starquakes. Are those a thing? Well, not exactly, but if you look at the circle of the planet here, you can tell that there is something going on. The patches we were discussing before, those convective regions, actually are regions that are keen to convective water that you see all the time that you boil a pan of water in the kitchen. So when you boil water, you see that after some time that you make heat emerging from the bottom of the pan, the water will start boiling in a very chaotic, noisy pattern. So what's happening is that energy needs to be transported upward, and the only way for energy to be carried out is for water to start moving in a turbulent manner and bringing heat outside and releasing at the surface of the pan when it's in contact with the air. Well, on the sun, something very similar happened. The only difference is that you can see here, the convective cells, akin to the convective cell that you see on the water pan, are much bigger. This is the size of US compared to the boiling pattern on the surface of the sun. So basically, just a few cells will encompass the whole country. Now, you know something important about convection in the kitchen, that this makes sound. There is noise coming. And as a matter of fact, you can tell if the water is boiling even if you're not in the kitchen by just the fact that you can hear the noisy sound of convection. So you know that this physical process creates sound waves. But sound waves are exactly those things that we want to use to probe the star. So those sound waves can propagate, as you can see in this movie, from the surface in the inner region of the star and come back. As they come back, they tell us something about the region they cross. So, the star becomes, in a sense, a huge musical instrument. Its sound, it plays certain notes, and listening to those notes, you're able to tell something about the musical instrument. You know very well that a cello sounds very differently than a violin, and the reason is that it has a different composition, different size, so the notes that they play, the pitch is different. But there is a problem with that, and I think you already noticed what I'm talking about here, is that, well, sound doesn't propagate in a vacuum. So there's no way for us to listen to the sound produced by the stars. So this is not viable. So what can we do about it? Well, there is a way. That is due to the fact that when a star oscillates due to the propagation of this sound, the gas, the plasma is just a fancy word for hot gas, by the way. The plasma is compressed and expanded as the wave passes by. But a compressed gas, as you know, it's hot, and when it expands, it becomes cool. Now, it turns out that on a star, when you compress the gas, you make it hot and bright, and when you expand it, you make it cool, which also means dimmer. So this movie is showing you a model of this kind of oscillations we're talking about, this kind of musical oscillations. Of course, the amplitude is exaggerated here for showing purposes, but the important thing is that the red and blue patches showing exactly what I was talking about, so the lower and higher temperature, which means that when you integrate the light coming from this oscillating object, the brightness fluctuates as a function of time. That means that, in a sense, the star is encoding by itself, by this oscillation, its own sound into the light it emits. So in a sense, the star becomes like a radio. The radio is doing exactly like that. When you hear music from the radio, what you're doing, you're listening to sound, but actually as being transported and carried around from electromagnetic waves, which are being encoded by the radio signal. This is the same here. The star oscillates. In a sense, it's sounding certain notes, but then these are encoded into light that crosses now large distances. You can see the light from distant stars. And then if you look at this brightness fluctuation, you can decode the sound of the stars and learn something about the musical instrument. To do that, you need to go in space. And the reason is that, as we'll see, this oscillation, the amplitude is very small. And so what we've been doing in the past is using the Kepler satellite, which is the satellite in orbit that is able to watch for several years hundreds of thousands of stars, looking for this brightness fluctuation at a small level, with a level of precision of a few parts in a million. And this is what Kepler saw. This is an example of the concert of stars. As you can see here in this plot, as a function of time, this is the fluctuation of brightness of these stars. So these are stars of different size, and you can see that different stars show different brightness fluctuation. The time scale, as you can see, is of order of days up to months. The reason is simple. Those stars are big, so are very big musical instruments. So the time it takes for this wave to cross them is very long, which results into long time scale for the fluctuation and therefore very low pitch sound. The relative intensity also small instead because, as we said, it's the order of part of 1 in 1,000. So you need to be out of the atmosphere to be able to appreciate those very subtle changes in the brightness fluctuations. Now, different stars sound differently because of their different size and different internal composition and properties. What happened is actually stars evolved and changed their structure, their internal structure. So their average density changes, the kind of fuel they burn in their core changes, all things we're interested about. This is called stellar evolution. For example, our own star, the sun, will live another 5 billion years in this current state, which is called the main sequence, which is when it's burning hydrogen in its core, and then will become a red giant. When it becomes a red giant, it changes completely its structure and will become very extended, and its core will become very dense. Now, this kind of change can be noticed by Kepler just by listening to the sound of these stars. And what I'm going to do now is play the sound that a star like the sun produces, and then what it will produce when it will become older, just by looking at stars that are more evolved than the sun. Now, as I told you before, the sound that a star produces has very low frequency. So it will not be in the audible range for humans. But what we do, we multiply everything by a factor so that it can fall into the range of audible spectrum. But the waveform is unaltered. So here's the sound of the sun. Now, when the sun will become a red giant initially, it will sound like this. And then later on, when it will become even bigger to the right, it will sound like this. Now, you cannot really tell much from this noisy background sound, but studying this music, scientists can tell a lot about what's going on in the star, its average density, its radius, its gravity, and so on. But of course, the stuff we're really interested in is looking deep down in the core. That's where all the action happens. And that's where surf waves enter. So that's where the game becomes interesting. So I want to spend one minute to tell you a little bit about surf waves, because this is not obvious. You all know about sound waves. Sound waves propagate through the air. There are perturbation in pressure. This is what has allowed me right now to talk to you. And this is when you play an instrument. That's what you do. You perturb the medium, and and that medium reacts with pressure perturbation, and you get the sound. For gravity waves, is a little different. Gravity waves are the restoring force is the gravity itself. And you experience gravity waves when you surf. Surf waves are a type of gravity waves. Or you've seen gravity waves when you're flying on a plane, looking at, for example, at the cloud or cloud patterns. As a note, these are different than gravitational waves. Gravitational waves, the one that just discovered, that you will hear about it in a little bit during the break. Those are ripples in the very fabric of space-time, different than gravity waves. Unfortunately, a very similar name, but that's it. Now, to do this stealth ultrasound that can even probe the renal regions, the very deep core, it turns out that we can use a very favorable situation that only occurs mostly in red giants, this bigger star we talked about a second ago. There, not only the sound waves that are excited by the turbulent convection at the surface propagate inward, these actually can resonate with these gravity waves that can exist in the core. So it's like somebody is playing the instrument outside, and the frequency of those waves become resonant with the instrument that resides inside the core of the star. And some energy can leak from the envelope to the core and play this instrument, and now it's playing into gravity waves. The resulting mode is called a mixed mode, and it can bring to the surface information about the core, because now the wave is propagating from the surface down to the core and coming back. So looking at these mixed modes, scientists can tell something about the very core of the star. And this is where it got interesting, because just last year, together with some collaborators here at UCSB, Caltech, and Sydney University, we decided to look at thousands of these stars and look at the notes that these stars were playing. So these stars all have this kind of mixed modes, so they are probing, these modes are probing the inner region of the star. And so what we did, we basically were tapping all these stars, thousands of them, listening to their sound, and trying to see if there was something weird about them. It's kind of astrofarming, because in a sense, this is what we do when you look at watermelon and you're trying to buy a good one. You tap it, you listen to the sound, and if you've done this a fair amount of time, you know that the sound will tell you something about the average density and the water content, which is telling you something about how ripe is the watermelon. And if you're a good farmer, you will know which one to pick. So we became good astrofarmers, and we recognized that this is the only plot I'm showing, by the way. So you don't need to know everything about here, but the only thing I want you to recognize is that every dot is a star in this plot. There's thousands of stars there, and on the y-axis is basically the visibility, which is a measure of how loud a note is being played. And you can see that there are two branches of stars. One branch here, 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 that show that these stars show pretty much the same amplitude of sound. And there's a branch instead that show that sound is kind of suppressed. That note doesn't play well. It's like somebody is holding the note down. So we identified that something was wrong with the star. Not wrong, but something different. And we found out that those stars had something in their core that was preventing those notes to play. And that turned out to be strong magnetic fields. So strong magnetic fields are similar to rubber bands, and what was happening is that those waves propagating into the core, the one that were made into the core, those mixed modes, will interact with these rubber bands, and the rubber bands will prevent those waves, those surf waves, to propagate through. And so those nodes were basically hampered. Magnetic fields that required to do this are very, very large. We're talking about 1 million times larger than the magnetic field on Earth, or 100,000 times larger than the magnetic field of a typical fridge magnet you might have at home. And so we learned that a large fraction of stars host this kind of fields, which was a complete novelty. And then there are at paramount implication for the evolution of the star and its death. Just to mention something, we believe that the brightest explosions in the universe, some of the brightest explosions in the universe, and the one that we can watch from the farthest distance, called long downward bursts,